This is our team's capstone presentation for Pokeclone DevOps Capstone Project by Pokeclone. So we have two links over here. The first one is a Docker and a Kubernetes repository, and second one is a Terraform repository. And next is our team's members. So the first one is Edwin Quito. He's from the Marines veteran. And second is Stephen Lamro. He's from Army veteran. And me, Xinxin Ho, from Army spouse. And here is our team's logo. It's really cool, right? Next is a project review. We deployed this web application, Pokeclone. This is for the education project developed by Platoon team. And also the Pokeclone is a 3-tier deployment, combining a React White front-end, a Django backend, and a PostgreSQL database. So we focus this project was to implement DevOps practice to automate, scale, and efficiently deploy the application on the AWS cloud infrastructure. To achieve this, our team employed a variety of technology including Terraform, Docker, Kubernetes, and various AWS services. So next, I'm going to my terminal to access my application using kubectl get all namespace Pokeclone to get all on my namespace. Here is my 2 ports. So first one is for the back end, second one is for the front end. To get access the application, I use the external IP that was generated by load balancer. I will copy and paste to show you the stack. So you can go ahead and sign up here if you guys want to. I already have an account, so let's go to the login here. So we can continue our game. So we have 3 house over here. The first one is a change Pokemon, second is a heal Pokemon, and third one is a battle gym leader. And also we have a grass over here. You can capture the Pokemon. So let's go to the first one, the change Pokemon.
Hello everyone. Today I'm going to go through over our AWS architecture diagram. So right here we have on the top WSL2 terminal, where holds our configuration files such as AWS account configs, our VPC, and EKS Terraform files. So where it begins is by our internet gateway. Our internet gateway will allow traffic from the internet to come through our VPC. Then our router's job is to route that traffic, and it allows our network load balancers to evenly distribute that traffic to our worker nodes. So we have 2 availability zones, and each availability zone has 1 public subnet and 1 private subnet. Our public subnet 2 has our Amazon RDS, and our public subnet 1 has our NAT gateway. The NAT gateway basically allows the private side to have internet access without being fully exposed. Our front-end nodes and our back-end nodes also have their own security group, and they have their own auto-scaling group. Security group has an extra layer of security to our worker nodes, and the auto-scaling group allows us to configure the desired size, minimum and maximum size of worker nodes. In our right-hand side, we have a couple of snippets of our Terraform code that we use to build our AWS infrastructure. I'm not going to go too in depth with it, but I am going to mention a couple key points. So for our virtual private cloud, we have our VPC, subnets, and internet gateway. As you can see, they're all being attached to the VPCs, as well as for the subset, it has its own setter block, which is just an IP range within the setter block already assigned to the VPC. We also have our EIP, which stands for Elastic IP, which is basically a permanent IPv4 address. So our NAT gateway, whenever we restart our services, it will just stay with the same IPv4. We also have a route table with a specific route. There's also this for my private route. This has a NAT gateway. So for our public, I'll have an internet gateway ID. Then for associating our subnet IDs to specific routes, we have AWS Route Table Association. Then we have our security groups, which basically controls our inbound and outbound traffic. And we have a configuration for our database as well, just basic configuration, which is just engine version, username, password, and so on and so forth. And we also need a database subnet group, which is basically a group of subnets where our database will either be at. Here is the most important part. These 3 snippets are not all of it, but it's for the most part what I think is pretty important for our EKS cluster creation. We have a role named Pokemon Demo. This will allow the EKS to assume the role. Once it assumes the roles, it will also assume the policies attached to the roles. On the bottom right here, we have our AWS EKS cluster, and ends up creating the cluster and attaches a role to it. So the cluster will have all the roles or policies within that role. Then we also have our VPC configuration. So we also have our subnet IDs, all four of them, two public and two private subnets. Same thing as for the EKS node group. We have a role specifically for our nodes and all the policies attached to the nodes. So those EC2 nodes will have specific permissions and can do specific things. Then we have our SNS topic and our subscription to that topic, which is we're using email, so we're getting email notifications. Then we have CloudWatch Metric Alarm, which will give us a email notification once it reaches a certain threshold or a certain event within our resources. And our dashboard just allows us to visualize everything that's happening within our resources, such as CPU utilization, a list of cluster, a list of nodes, and so on and so forth. This is just was shown in our AWS console and how our network is configured, VPC, subnets, route tables, and network connections. You can see how they're all thoroughly connected. This just shows that our database is up and running, and also our event bridge is doing its job by doing a scheduled DB snapshot. Here we have our event bridge. Event bridge is scheduled for every 10 minutes to create a database snapshot, but since this is just for a test deployment, I put it as 10 minutes, but it will be changed to weekly or whatever the priorities are set for. We also have our SNS topics that are being created, auto-scaling groups, alarms, database snapshot, event topic, EKS cluster alarms. This is just a Pokemon cluster. I can't show a lot of it since it has a lot of sensitive information. So this is the most I could show, but it does show that our cluster is actually active. And here is just our monitoring dashboard. Just allows us to visualize everything that's happening within our resources, just as the EKS list of EKS cluster, list of nodes, logs, CPU utilization, and so on and so forth. All right, I'm handing back to Zinzin and Steven. Thank you very much.
Yes, containerization with the Docker. So we decided use the Docker, the reason being consistencies across environments. It ensures the application run the same in every environment. Isolation. Containers are isolated from each other, so that enhance the security and reduce the application conflicts. And then the resource efficiency is more efficient than virtual machines. Rapid deployment and scaling. It's easy to scale up or down based on the demand. The last one is version control and rollback. The images can be versioned and stored for the easily rollback. Next, we utilize Kubernetes for automate the deployments, scaling, and the management of containerized applications. It ensuring they run efficiently and resiliently. The key benefits we have scalability, high availability, load balancing, self-healing, and configuration management. Now we have all of our infrastructure set up, so we want to do some automation to update the code. Whenever someone updates the code, it automatically tests and prepares the code to be released. So we don't have to manually do this task. Push to the EKS RDS branch. The first job is front end and back end Docker images are built. Next, these images are securely pushed to the Docker Hub. This step makes our images available for deployment and ensures we have versioning for rollback if needed. And next, the pipeline then update the kube config on our EKS cluster. These important steps ensure our Kubernetes cluster is always configured with the correct access permission for deployment. Following this, all Kubernetes deployment files are applied to the cluster. This step relies on our application in the live environment, setting up the service, deployments, and more. So finally, the Django migration applied automatically. This ensures our database schema is always in sync with our application requirements. I will pass to the Stephen to go over the details.
So the way that we deployed this app was through multiple stages. The first one being deploying it locally. This gave us the opportunity to make sure that the app worked correctly, and just get a little more familiar with the code base since we've never seen this app before. Basically, the front end was running off the Node server and it was making the API calls to the Django backend, and that was connecting to my local Postgres database. And then I would access it through the web browser, a local host. To do this, it just required setting up a Python virtual environment, installing some dependencies, and I had to create the database manually. The only other thing needed was the Django secret key, and that was placed in an env file. After that, we just had to migrate the Django files for the backend database. And then if you wanted to use the admin panel, you can create a super user. After that, you're just going to run the backend, and moving over to the front end, you're going to run your npm install command and then run your local dev server, which was using 5173 for the port since it's with Vite. And that was all it took to get this running locally. Our next step in the deployment takes us to using Docker, where we deployed it using Compose. As you can see in the diagram, each section of the app here is in its own container. And it starts off with the front end making a call to the back end. And the back end is using the Postgres env variables to access the database, which then in turn sends its data back to the back end and to the front end, where you can view it on the web browser using localhost 8080. So now instead of 5173, we're on 8080 because that's what Nginx is being forwarded to. The Docker files consist of we have a back end and a front end. It starts off with this syntax line. It allows us to use the latest Docker file version without having to upgrade the Docker engine itself. So if you were ever using an older version, you can still use the latest front end for Docker. From here, we're pulling in the minimal Python Alpine image and creating a worker. I'm going to take our requirements.txt file, copy it, and run the pip install command. The reason why we have two copy commands is Docker has a built-in caching. So if there are no changes made to your dependencies here, and you make changes to your app, it's not going to run this command over again because it knows nothing has changed with the requirements. We're going to set our environment variable. That's our Django secret key. And 8000 is the port that Django's using. So we're going to make sure to expose that. To run our server, we're going to use the command. The front end is using Node. We're using a two-step build here where it's going to have the full Node version with Node latest. And then later on, it's going to use the minimal Alpine version. Same thing as before, we have the multiple copy commands to use caching, where we're installing all of our dependencies. And we're going to run Nginx to serve our front end here. Moving into the compose file, it's going to have all three tiers, starting with our database. We're just pulling in the standard Postgres image and creating a couple volumes to use with it down here. So we have data and config for our volumes and setting our mandatory Postgres variables that we need. And the database is going to be on its own network that only the backend can connect to. So leaving the front end out of it. And it's also going to rely on a health check for the database to be running correctly before anything else can launch. So to see here, the next step with the backend, it's going to rely on the healthy database. It's going to set its environment variables. The port is 8000, like we said before. And this is the same Python run server command that we've been using to launch our backend. And then the front end is going to use that front end Docker image, and we're going to send it to port 8080 on our end. So 80 on the host and 8080 on the client. And that pretty much covers the compose build. Now we move on to the Minikube now, where we're using Kubernetes for all the container orchestration. And it's a good way to test out your code before you move on to a production environment like EKS. So the difference here is we are using a single Docker file. We just wanted to test out different ways that we can deploy the app. So now instead of a front end container, this turns into a 2-tier deployment where the front end static files are being served through Django now instead of Nginx. And to do this, we use a app called White Noise. And you can see a little better with the diagram is, starting off at the developer machine, I have all the Kubernetes manifest files here. And you apply these in order, starting with the namespace and the quota. And we move on to the database. And then the backend is going to serve the front end files. So the database is going to have its own, config map and secrets. So, things like passwords are not in plain text. Those would usually be get ignored, but I left that here for demonstration purposes. Then we have our volume and volume claims. And the backend also has its own config map and secrets. Our next step was finally deploying this onto Amazon EKS, which is a managed Kubernetes service that just makes your life a lot easier when deploying Kubernetes applications to the cloud. The way that this deployment is triggered is through a GitHub Actions CI/CD. And this is going to check out our repo, set up the Docker build, log into the account, and push any changes to Docker Hub for the images. After that, it's going to configure the credentials we use for AWS, update kubeconfig so we can run the kubecontrol commands, and it's going to deploy all of our manifest files to EKS. And so now, similar to before, we have all the namespace and quota and all the same containers and files, but they're all on a Kubernetes cluster, EKS. And then the front end is going to be accessed through a load balancer URL now. And finally, our last build, pretty much the same as before with the EKS deployment, except now we're using a RDS database instead of our own. So as you can see, the diagram hasn't really changed, except now it's pointing to an Amazon RDS database, which for us, it gets rid of that entire database file directory I had. Well, it's still here, but it gets rid of all these files now. So Amazon's going to take care of all the persistent data and the configs and secrets and everything. So now in the GitHub action, when it's pushing these files, it's not going to bother deploying the database section anymore. And that about wraps up the overview for each step of our deployment process.